Time is not what you think it is. You experience time as a river, flowing steadily from past to future, carrying you along whether you wish to go or not. You wake up, you live your day, you go to sleep. Tomorrow arrives, as it always does, following today as certainly as effect follows cause. This is time as you know it, constant, predictable, inescapable. This intuition is wrong, not slightly wrong, fundamentally wrong. Time is stranger than your brain can fully comprehend, stranger than evolution equipped you to understand. And yet, despite its strangeness, despite the bizarre revelations of modern physics, one thing remains clear. You will never travel through time the way you imagine. I have spent my life exploring the cosmos and the laws that govern it. I have studied relativity and quantum mechanics, black holes and the origin of the universe. I have imagined journeys to distant stars and speculated about civilizations beyond our own. And I can tell you, with the full weight of everything physics has taught us, that traveling backward in time is almost certainly impossible. Not merely difficult, not awaiting some future technology. Impossible in principle, forbidden by the deepest laws of nature. This is not a limitation we can engineer around. This is not a problem that cleverness will solve. This is the universe telling us no. Let me explain why. First, let me tell you what time actually is, because your intuitions will mislead you at every turn. Before Einstein, we thought time was absolute. Newton imagined a cosmic clock ticking away in the background of the universe, measuring moments that passed identically for everyone, everywhere. A second on Earth was the same as a second on Mars, the same as a second in the most distant galaxy. Time was the stage on which events occurred, unchanging and universal. Einstein destroyed this idea in 1905. His special theory of relativity revealed that time is not absolute, it is relative. It depends on how you are moving. This sounds abstract. Let me make it concrete. Imagine you are standing on Earth, watching a spacecraft fly past at 90% of the speed of light. You have a clock. The spacecraft has an identical clock. According to you, the spacecraft's clock is running slow, dramatically slow. For every second that passes on your clock, only about 0.44 seconds pass on the spacecraft's clock. This is not an illusion. This is not a measurement error. This is reality. Time itself runs slower for objects moving at high velocities relative to you. But here is the strange part. From the perspective of the astronaut on the spacecraft, your clock is running slow. You are the one moving relative to them. You are the one experiencing dilated time. Both perspectives are equally valid. Both are correct. How can both observers see the other's clock running slow? This seems paradoxical, impossible, a contradiction at the heart of physics. But it is not a contradiction. It is a consequence of the fact that simultaneity itself is relative. Events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first. Time is not a river flowing at the same rate everywhere. Time is a dimension woven together with the three dimensions of space into a four-dimensional fabric called spacetime. And this fabric can be stretched, compressed, and warped by motion and by gravity. This is not philosophy. This is measured fact. We have tested time dilation with atomic clocks flown on aircraft. We have confirmed it with particles accelerated to near light speed. We have verified it with GPS satellites, which must account for relativistic effects to provide accurate positioning. Time dilation is real. It happens. The universe actually works this way. Now, you might think this opens the door to time travel. If time can run at different rates, perhaps it can run backward. If we can slow time down, perhaps we can reverse it. This is where the universe closes the door. Time dilation allows you to travel into the future. This is not speculation. This is established physics. If you accelerate to a significant fraction of the speed of light, travel for what seems to you like a few years, and return to Earth, you will find that decades or centuries have passed. You have traveled into the future. You have skipped over time that you did not experience. The astronauts on the International Space Station experience this in a tiny way. Because they are moving faster than people on Earth's surface, their clocks run slightly slower. After a year in orbit, they have aged about 0.01 seconds less than people on Earth. They have traveled 0.01 seconds into the future. This effect becomes dramatic at velocities approaching light speed. If you could travel at 99.99% of light speed, time dilation would be so extreme that 1 year of your experience time would correspond to about 70 years on Earth. You could leave today, travel for a decade by your clock, and return to find everyone you knew dead for centuries. This is time travel into the future. It is allowed by physics. It requires enormous energy and engineering we do not possess, but it violates no fundamental laws. With sufficient technology, you could do it. But traveling into the past is different. Traveling into the past is not merely difficult. It appears to be forbidden by the structure of reality itself. Let me explain why, starting with causality. Causality is the principle that causes precede effects. You throw a ball, and then it moves through the air. The throwing causes the motion. The motion does not cause the throwing. This ordering seems so obvious that it hardly needs stating. Of course, causes come before effects. How could it be otherwise? But traveling backward in time would violate causality. If you could travel to the past, you could make an effect precede its cause. You could arrive at a destination before you departed. You could answer a question before it was asked. You could prevent an event before it occurred. This leads immediately to paradoxes. The most famous is the grandfather paradox. Suppose you travel back in time and kill your grandfather before he meets your grandmother. Then your parent is never born. Then you are never born. But if you are never born, you cannot travel back in time to kill your grandfather. But if you don't kill your grandfather, you are born, and you do travel back in time, and you do kill him. The logic spirals into contradiction. Some people dismiss this as a mere puzzle, a brain teaser that surely has some clever solution. Perhaps you cannot actually change the past. Perhaps whatever you do when you travel back in time was always part of history. Perhaps you were always going to travel back, and your actions were always going to occur, and there is no paradox, because nothing actually changes. This is the idea of a self-consistent timeline. Everything that happens when time travelers visit the past was always part of history. Your presence in 1920 was always part of 1920. You cannot change anything because everything you do was always done. This sounds elegant, but it creates its own problems. It implies that free will is an illusion, at least for time travelers. You cannot choose to do anything that was not already part of history. You are constrained by the future that has already occurred to make the choices that were always made. More troublingly, self-consistent timelines raise the question of where information comes from. Suppose you travel back in time and give Shakespeare the complete works of Shakespeare. Where did those works originate? Shakespeare didn't write them. You gave them to him, but you only had them because Shakespeare wrote them. The information has no origin. It exists in a closed loop, coming from nowhere, violating something that feels fundamental about how the universe should work. These paradoxes are not proof that backward time travel is impossible. They are hints. They are the universe waving red flags, warning us that something is deeply wrong with the concept. But the real prohibition comes from physics, not philosophy. Let me tell you about the second law of thermodynamics, because this law may be the ultimate barrier to backward time travel. The second law states that entropy, a measure of disorder, always increases in closed systems. Heat flows from hot objects to cold objects, concentrated energy disperses, order dissolves into chaos. This is not merely a tendency. It is a law so fundamental that it defines the direction of time itself. Think about what happens when you drop an egg. It falls, hits the floor, and shatters. The ordered structure of the shell breaks into disordered fragments. The concentrated yolk spreads across the floor. Entropy increases. Now imagine the reverse. Scattered fragments of shell leap from the floor, reassemble into a perfect egg, which then rises into your hand. Yolk flows back into its membrane. Water spontaneously emerges from chaos. Entropy decreases. You have never seen this happen. No one has ever seen this happen. It violates no law of mechanics. Every individual collision of every individual atom could, in principle, run backward. But the probability of all those atoms spontaneously coordinating to reassemble the egg is so vanishingly small that it effectively never occurs. The number is so close to zero that writing it down would require more zeros than there are atoms in the observable universe. This is why time has a direction. This is why we remember the past but not the future. This is why causes precede effects. The second law of thermodynamics creates an arrow of time, pointing from low entropy to high entropy, from order to disorder, from past to future. Backward time travel would mean reversing this arrow. It would mean going from high entropy to low entropy, from disorder to order, from future to past. It would mean violating the most fundamental asymmetry in the universe. Some physicists argue that the second law is statistical, not absolute. In principle, entropy can decrease spontaneously. It's just overwhelmingly improbable. Perhaps a sufficiently advanced technology could somehow coordinate matter and energy to reverse the entropic flow. I find this unconvincing. The second law has been tested more thoroughly than any other principle in physics. Every time we think we've found a violation, closer examination reveals that entropy increased somewhere we weren't looking. The law holds. It always holds. It is as close to absolute as anything in science. And even if you could somehow locally reverse entropy, the paradoxes would remain. Causality would still be violated. Information would still appear from nowhere. The logical contradictions that arise from backward time travel do not depend on thermodynamics alone. The universe seems to be constructed at the deepest level to prevent travel into the past. Multiple independent principles, causality, thermodynamics, the structure of space-time, all point in the same direction, all say no. Let me tell you about what Einstein's general theory of relativity says about time, because this is where the hope for time travel seems brightest and where that hope ultimately dies. In 1915, Einstein extended his special theory of relativity into something far more profound. He showed that gravity is not a force in the traditional sense. Gravity is the curvature of space-time itself. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move. This sounds abstract, so let me give you an image. Imagine a stretched rubber sheet pulled taut in all directions. Now place a bowling ball in the center. The sheet curves around the ball, creating a depression. If you roll a marble across the sheet, it doesn't travel in a straight line. It curves toward the bowling ball, following the contour of the surface. This is what mass does to space-time. The sun curves space-time around it. Earth doesn't orbit the sun because of an invisible force pulling it. Earth orbits because it is following the straightest possible path through curved space-time, and that path happens to be an ellipse around the Sunday. Now, here is where it gets interesting for time travel. Space-time is four-dimensional. 3 dimensions of space, 1 dimension of time. When mass curves space-time, it curves both space and time. Near a massive object, time runs slower. This is not the same as the time dilation from velocity that I described earlier. This is gravitational time dilation, a separate effect predicted by general relativity and confirmed by experiment. A clock on the surface of Earth runs slightly slower than a clock in orbit. Because the surface is deeper in Earth's gravitational well, a clock on the surface of the sun would run even slower. A clock near a black hole, where gravity is extreme, would run dramatically slower compared to a clock far away. This has been measured with extraordinary precision. The GPS satellites I mentioned earlier must account for both velocity-based time dilation and gravitational time dilation to function correctly. Without these corrections, GPS would accumulate errors of kilometers per day. The fact that GPS works is proof that Einstein was right. So gravity warps time. Extreme gravity warps time extremely. What happens if you warp time enough? Could you warp it so severely that it bends back on itself, creating a loop? This is the tantalizing possibility that general relativity seems to offer. If space-time can curve, perhaps it can curve so much that the future connects to the past. Perhaps there are configurations of matter and energy that create what physicists call closed time-like curves, paths through space-time that return to their own past. Several such configurations have been proposed. Let me describe the most famous ones and explain why none of them offer real hope for time travel. The first is the rotating universe solution discovered by mathematician Kurt Gödel in 1949. Gödel showed that if the entire universe were rotating, general relativity would allow closed time-like curves. You could travel in a sufficiently large circle and return to your own past. This is mathematically valid. Einstein himself was disturbed by Gödel's solution because it seemed to imply that backward time travel was permitted by general relativity. But there is a problem. Our universe is not rotating. Observations of the cosmic microwave background radiation confirm that the universe has essentially zero net rotation. Gödel's solution describes a universe that is not ours. The second proposal involves infinitely long rotating cylinders discovered by physicist Frank Tipler in the 1970 seconds. If you had a cylinder of infinite length rotating at tremendous speed, the space-time around it would be dragged in a way that creates closed time-like curves. You could travel around the cylinder and return to your past. But the cylinder must be infinitely long, not very long. Infinitely long. There are no infinitely long objects in the universe. There cannot be, because the universe itself is finite in age and therefore finite in extent in certain directions. Tipler's cylinder is a mathematical curiosity, not a blueprint for a time machine. The third and most famous proposal involves wormholes. A wormhole is a hypothetical tunnel through space-time connecting two distant points. Imagine folding a piece of paper so that two points touch, then punching a hole through both points. The hole is a shortcut, allowing travel between the points without crossing the intervening space. Wormholes are permitted by general relativity. The mathematics allows them. And in 1988, physicist Kip Thorne showed that if you could create a wormhole and then move one end of it at high velocity, the time dilation effects could convert the wormhole into a time machine. Enter one end, exit the other end in your own past. This generated enormous excitement. Here, finally, was a mechanism for backward time travel that didn't require an infinite cylinder or a rotating universe. Just a wormhole and some clever manipulation of its endpoints. But there are problems. Severe problems. Problems that almost certainly make wormhole time machines impossible. First, we have never observed a wormhole. Not one. Despite decades of searching, despite theoretical predictions about where they might exist, we have found no evidence that wormholes occur naturally anywhere in the universe. They are allowed by the mathematics, but mathematics allows many things that don't exist. Second, wormholes are unstable. Any wormhole that formed naturally would collapse almost instantaneously, far too quickly for anything to pass through. To hold a wormhole open long enough to traverse it, you would need exotic matter, matter with negative energy density. Negative energy density is strange. Ordinary matter has positive energy. Even antimatter has positive energy. Negative energy density would require something that has less energy than empty space itself, something that gravitationally repels rather than attracts. The existence of such matter is not prohibited by known physics, but it has never been observed, and there are strong theoretical reasons to believe it cannot exist in the quantities needed to stabilize a wormhole. The Casimir effect, a quantum phenomenon where parallel conducting plates experience a tiny attractive force, is sometimes cited as evidence that negative energy can exist. But the Casimir effect produces fantastically small amounts of negative energy density, nowhere near enough to stabilize a wormhole. Scaling up the effect to useful levels appears to be impossible. Third, Even if you could somehow create a stable wormhole and convert it into a time machine, quantum mechanics may intervene to prevent it. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent closed time-like curves from forming. Hawking's reasoning was based on quantum field theory. When you try to create a closed time-like curve, quantum vacuum fluctuations become amplified. As the would-be time machine approaches the moment when it would become operational, the energy density of these fluctuations grows without bound. Before the time machine can actually work, the energy becomes so intense that it destroys the wormhole or whatever mechanism was supposed to create the closed time-like curve. This has not been rigorously proven. Quantum gravity, the theory that would fully describe what happens in such extreme situations, does not yet exist. But the chronology protection conjecture is consistent with everything we know about physics. The universe appears to defend causality. It appears to have built-in mechanisms that prevent backward time travel from being achieved. Let me tell you about another approach to time travel that has been proposed using the intense gravitational fields of rotating black holes. A rotating black hole, described by the Kerr solution to Einstein's equations, has a fascinating internal structure. Unlike a non-rotating black hole, which has a point-like singularity at its center, a rotating black hole has a ring-shaped singularity. And the mathematics suggests that if you could pass through this ring, you might enter a region where closed time-like curves exist. You might be able to travel into the past. This sounds promising until you examine the details. First, to reach the ring singularity, you must pass through the event horizon of the black hole. Once you cross the event horizon, you cannot return. You are falling inexorably toward the center. Even if closed time-like curves exist inside the black hole, you cannot use them to return to the external universe. You are trapped. Second, the interior of a real black hole is probably nothing like the idealized Kerr solution suggests. The Kerr solution describes an eternal, unchanging black hole in a universe with no other matter. Real black holes form from collapsing stars. They exist in a universe filled with matter and radiation. The actual interior structure is likely far more complicated and violent than the elegant mathematics suggests. Third, even if you could somehow survive the passage through the event horizon and navigate the interior geometry, you would encounter another problem. The inner horizon of a Kerr black hole, the boundary beyond which closed time-like curves might exist, is unstable. Any perturbation, any matter or radiation falling into the black hole causes the inner horizon to become a region of infinite energy density. You would be destroyed before reaching the region where time travel might be possible. Every door that general relativity seems to open, the universe closes with another mechanism. Wormholes collapse. Rotating cylinders must be infinite. Rotating universes don't match observations. Black hole interiors are deadly and unstable. Quantum effects destroy would-be time machines before they can operate. This is not coincidence. This is the universe telling us something fundamental about its structure. Backward time travel is not merely difficult to achieve. It is forbidden at a deep level. Let me tell you about the grandfather paradox from a physicist's perspective. Because the logical contradictions are not separate from the physical impossibilities. They are connected. Physics describes the universe as evolving according to consistent laws. Given the state of a system at one time, the laws determine the state at future times. This is determinism, and it works in both directions. Given the state at a later time, you can in principle calculate the state at earlier times. But if closed time-like curves exist, this consistency breaks down. You can create situations where no consistent history is possible. The grandfather paradox is the most famous example, but there are many others. Any situation where your actions in the past prevent the conditions that led to your time travel creates a logical contradiction. Some physicists have proposed that consistency is enforced automatically. The universe simply doesn't allow paradoxical situations. If you travel to the past, something always prevents you from causing a paradox. Your gun jams, you slip and fall. A meteor strikes you. Whatever it takes, the universe conspires to maintain consistency. This is the Novikov self-consistency principle. It preserves the logical structure of physics, but at a strange cost. It implies that free will is constrained for time travelers. You cannot choose to cause a paradox, because physics itself prevents paradoxical choices from succeeding. Most physicists find this unsatisfying. It requires a kind of cosmic censorship that has no known mechanism. How does the universe know that your action would cause a paradox? How does it intervene to prevent it? What physical force implements this consistency requirement? The simpler conclusion, the one that most physicists draw, is that backward time travel is impossible. The paradoxes don't arise because you can't cause them. You can't cause them because you can't travel backward in time. The contradiction points to a fundamental prohibition, not to a clever mechanism for avoiding contradictions. Physics works. It is consistent. It makes predictions that are confirmed by experiment. If backward time travel led to inconsistencies, that would undermine the entire enterprise of physics. The fact that physics works is evidence that backward time travel doesn't happen. This is not a formal proof. Perhaps there is some way to resolve the paradoxes that no one has thought of. Perhaps the universe has mechanisms we don't understand. But the simplest interpretation of everything we know about physics is that the past is fixed. It cannot be changed. It cannot be visited. It is gone. Let me tell you about quantum mechanics, because some people believe that the strangeness of the quantum world might offer an escape from the classical prohibitions against time travel. It does not. If anything, quantum mechanics makes backward time travel even more problematic. Quantum mechanics is the physics of the very small, the theory that describes atoms, electrons, photons, and the fundamental constituents of matter. It is strange beyond anything our intuitions prepare us for. Particles exist in superpositions of multiple states until they are observed. Measurements produce random outcomes governed by probability rather than certainty. Distant particles can be entangled, their properties correlated in ways that seem to defy locality. This strangeness has led some to hope that quantum mechanics might allow what classical physics forbids. Perhaps quantum superposition could resolve the grandfather paradox. Perhaps you could exist in a superposition of having killed your grandfather and not having killed him. Perhaps the quantum world is weird enough to accommodate time travel. This hope is misplaced. Let me explain why. First, quantum mechanics does not actually violate causality. This is a common misconception. Quantum entanglement, the phenomenon where measurements on distant particles are correlated, seems to involve instantaneous influence across space. But it does not. You cannot use entanglement to send information faster than light. You cannot use it to signal the past. The correlations are real, but they cannot be exploited for communication. This has been proven rigorously. The no communication theorem demonstrates that quantum mechanics, despite its strangeness, respects causality. Effects do not precede causes. Information does not travel backward in time. The arrow of causation points in one direction only. Second, quantum mechanics actually strengthens the case against backward time travel through something called the quantum no-cloning theorem. The no-cloning theorem states that you cannot make a perfect copy of an arbitrary quantum state. This sounds technical, but its implications are profound. Information in quantum mechanics is fundamentally different from classical information. Classical information can be copied freely. You can duplicate a book, a file, a message without limit. Quantum information cannot be copied. It is unique, it can be moved, but not duplicated. Now consider what backward time travel would imply. If you travel to the past, there would be two copies of you. The younger you who hasn't yet time traveled, and the older you who has arrived from the future. The older you carries information, memories, knowledge of the future. If this information is encoded in quantum states, as all physical information ultimately must be, then backward time travel would violate the no-cloning theorem. This is not a definitive proof. Perhaps the information could be transferred rather than copied. Perhaps the younger you would somehow be absorbed into the older you. But the no-cloning theorem adds another obstacle to an already formidable list. It suggests that quantum mechanics, far from enabling time travel, provides additional reasons why it cannot occur. Third, there is the quantum arrow of time. I mentioned earlier that the second law of thermodynamics creates an arrow of time at the macroscopic level. But there is also a quantum arrow of time related to the measurement process itself. When a quantum measurement occurs, the wave function collapses. A particle that was in a superposition of many states suddenly assumes a definite state. This process is irreversible. You cannot uncollapse a wave function. You cannot unmeasure a measurement. The information about the prior superposition is lost. This irreversibility is another manifestation of time's asymmetry. It operates at the most fundamental level of physics. Backward time travel would require reversing this process, recovering information that quantum mechanics says is fundamentally unrecoverable. Some physicists have proposed interpretations of quantum mechanics that avoid wave function collapse. The many worlds interpretation, for example, suggests that all possible outcomes of a measurement actually occur, each in a separate branch of a vast multiverse. Perhaps time travel could work by moving between these branches rather than within a single timeline. This is the idea behind the many worlds resolution of the grandfather paradox. You travel to the past and kill your grandfather, but you're not killing your grandfather. You're killing a copy of your grandfather in a parallel universe. Your own timeline remains consistent. You simply end up in a different branch of the multiverse. This is clever, but it's not really time travel in any meaningful sense. You're not returning to your own past. You're visiting a parallel universe that resembles your past. Your own history, the timeline you came from, remains unchanged. The grandfather you grew up with is still alive in your original branch. You have simply moved sideways in the multiverse rather than backward in time. More importantly, the many worlds interpretation, while mathematically consistent, is far from established science. It is one of several competing interpretations of quantum mechanics. We have no experimental evidence that parallel universes exist. We have no way to test the hypothesis. It may be true, it may be false, we simply don't know. Building hopes for time travel on speculative interpretations of quantum mechanics is building on sand. We cannot use unproven theories to circumvent proven prohibitions. Let me tell you about another quantum phenomenon that has been proposed as a mechanism for time travel: quantum tunneling. Quantum tunneling allows particles to pass through barriers that classical physics says they cannot penetrate. An electron encountering a wall of potential energy can sometimes appear on the other side, even though it never had enough energy to climb over the wall. It tunnels through as if the barrier weren't there. This is real. It has been observed countless times. It is essential to many technologies, including the scanning tunneling microscope and certain types of semiconductor devices. Some have wondered whether quantum tunneling might allow particles to travel backward in time. If a particle can tunnel through a barrier in space, perhaps it could tunnel through a barrier in time. The answer is no. Quantum tunneling does not violate causality. When physicists carefully analyze tunneling events, they find that no information travels faster than light. The particle does not actually traverse the barrier instantaneously. The mathematics of tunneling is fully consistent with relativistic causality. Experiments have been conducted to test whether quantum tunneling allows superluminal communication. They have consistently found that it does not. The tunneling process, strange as it is, respects the cosmic speed limit and the arrow of causality. Let me tell you about one more quantum phenomenon that sometimes appears in discussions of time travel: virtual particles. In quantum field theory, empty space is not really empty. It seethes with virtual particles, pairs of particles and antiparticles that pop into existence for brief moments and then annihilate. These virtual particles are a consequence of Heisenberg's uncertainty principle, which allows energy to be borrowed from the vacuum for short periods. Some interpretations suggest that virtual antiparticles can be viewed as particles traveling backward in time. An anti-electron, a positron, can be mathematically described as an electron moving backward through time. This was noted by Richard Feynman and is a useful computational tool in quantum electrodynamics. But this is a mathematical convenience, not a physical reality. Virtual particles are not real particles. They cannot be directly observed. They cannot carry information. They are terms in a calculation, not objects that travel through time. The positron interpretation as a backward-in-time electron is a formalism that simplifies calculations. It does not mean that anything actually travels backward in time. When we observe positrons in the laboratory, they are moving forward through time, just like everything else. The mathematical description that treats them as backward-traveling electrons is just one way of writing the equations. Quantum mechanics is strange. It violates many intuitions we have about how the world should work. But it does not violate causality. It does not allow information to travel backward in time. It does not open a door to changing the past. If anything, quantum mechanics reinforces the barriers against backward time travel. The no-cloning theorem, the quantum arrow of time, the consistency of quantum field theory with relativistic causality, all of these point in the same direction. Time flows one way. The past is gone. It cannot be revisited. Let me tell you about the information paradox, because it illustrates how seriously physicists take the consistency of time's direction. When matter falls into a black hole, it disappears from the observable universe. The black hole's event horizon is a one-way boundary. Nothing that crosses it can return. The information carried by the infalling matter seems to be lost forever. But quantum mechanics says that information cannot be destroyed. This is a fundamental principle as basic as conservation of energy. Information can be scrambled, hidden, transformed beyond recognition, but it cannot be eliminated. Every process in quantum mechanics is, in principle, reversible. Information is conserved. This creates a paradox. Black holes seem to destroy information. Quantum mechanics says information cannot be destroyed. Something has to give. This black hole information paradox has occupied some of the best minds in physics for decades. Stephen Hawking initially argued that information is truly lost in black holes, which would imply a fundamental violation of quantum mechanics. Most physicists found this unacceptable. Information conservation is too central to the structure of physics to be casually abandoned. Eventually, Hawking conceded. He acknowledged that information is probably preserved, though the mechanism remains unclear. The current consensus is that information somehow escapes from black holes, perhaps encoded in the Hawking radiation that black holes emit, though the details are still debated. Why am I telling you about the black hole information paradox in a discussion of time travel? Because it shows how seriously physicists take the consistency of temporal processes. If information could be destroyed, the past would become fundamentally uncertain. We could not in principle reconstruct earlier states from later states. The laws of physics would lose their time reversal symmetry at the deepest level. Physicists have resisted this conclusion with enormous effort. They have spent decades trying to resolve the information paradox precisely because the alternative, accepting that information can be lost, would undermine the logical structure of physics. The same concern applies to backward time travel. If you could travel to the past and change it, information would not merely be lost, it would be contradicted. The information in your memory would conflict with the information in the world around you. The universe would contain mutually incompatible records. This is worse than information loss. This is information inconsistency. And physicists find it even more unacceptable. The universe appears to be logically consistent. The laws of physics, quantum mechanics, and general relativity are mathematically consistent frameworks. They describe a universe where events follow from prior events according to definite rules. Backward time travel would introduce inconsistencies that undermine this entire structure. I believe this is the deepest reason why backward time travel is impossible. Not because we lack the technology, not because the energy requirements are too high, but because backward time travel would make the universe logically incoherent, and the universe, whatever else it is, appears to be coherent. Let me tell you about the future, because traveling to the future is a different matter entirely, and understanding why future travel is possible while past travel is not reveals something profound about the nature of time itself. I have said that backward time travel appears to be forbidden by the laws of physics. But forward time travel is not merely possible, it is inevitable. You are doing it right now. You are traveling into the future at a rate of 1 second per second, carried along by the relentless flow of time that governs all things. But physics allows you to travel faster than this, much faster. The time dilation effects I described earlier, arising from both velocity and gravity, allow you to reach the future while skipping over the intervening time. This is not science fiction. This is established physics, confirmed by countless experiments. Let me describe what this would actually look like. Suppose you board a spacecraft capable of accelerating continuously at 1g, the same acceleration you feel standing on Earth's surface. This would be comfortable. You would feel normal weight throughout the journey. You could walk, eat, sleep, live normally as the spacecraft carried you through the cosmos. At 1g of continuous acceleration, you would reach remarkable velocities surprisingly quickly. After 1 year of ship time, you would be traveling at about 77% of the speed of light. After 2 years, about 97%. After 3 years, about 99.5%. The closer you approach light speed, the more time dilation affects you. If you accelerated at 1g for 10 years of your experience time, turned around and decelerated at 1g for another 10 years, returning to Earth, you would find that you had aged 20 years. But Earth would have aged approximately 24,000 years. 24,000 years. That is the span from the last ice age to today. You could leave Earth as it is now and return to a world so transformed that it would be unrecognizable. Civilizations would have risen and fallen. Languages would have evolved beyond comprehension. The continents themselves would have shifted measurably, and you would have experienced only 20 years. This is time travel into the future. Real, physical, permitted by the laws of nature. The energy requirements are enormous, far beyond our current capabilities. Maintaining 1g of acceleration for years would require propulsion systems we do not know how to build. But there is no law of physics that forbids it. Given sufficient technology, you could do this. Now consider what this means for the asymmetry between past and future. You can travel to the future by moving fast or by sitting in a strong gravitational field. Time will pass slowly for you while it passes quickly for everyone else. When you emerge from your journey, the future will have arrived. But you cannot reverse this process. You cannot travel to the past by moving fast in some other direction or by sitting in some exotic gravitational field. The same physics that permits future travel prohibits past travel. Why? What is the difference? The difference is entropy. The difference is causality. The difference is the fundamental asymmetry built into the structure of the universe. When you travel to the future via time dilation, you are not violating any physical law. You are simply taking a different path through space-time, a path that covers less time than the paths taken by people who remained on Earth. Your personal entropy continues to increase. Causes continue to precede effects. The arrow of time continues to point in the same direction. You are just moving along that arrow at a different rate. Traveling to the past would require reversing the arrow. It would require entropy to decrease. It would require effects to precede causes. It would require the fundamental structure of physical law to work backward. The universe does not do this. The universe cannot do this, as far as we can tell. The asymmetry is built in at the deepest level. Let me tell you about the practical implications of future time travel, because they are interesting and perhaps disturbing. If you could travel to the future via time dilation, you would face a profound isolation. Everyone you knew would be dead, the society you left would be gone, the language might have changed, the culture would certainly have changed. You would be a stranger in a strange time, with no way to return to the world you left behind. This is not a technical problem. This is a fundamental consequence of how time dilation works. You can only go forward. You can skip over time, but you can never go back. The people you leave behind will age and die while you remain young. When you emerge from your journey, they will be dust. Science fiction often treats time travel as a way to see different eras, to visit the past and the future like a tourist visiting foreign countries. But real physics does not permit this. Real physics allows you to become a refugee from your own time, cast forward into an unknown future, permanently separated from everyone and everything you knew. Would anyone choose this? Under what circumstances would forward time travel be desirable? One scenario involves terminal illness. If you have a disease that is incurable today but might be curable in 100 years, time dilation offers a form of suspended animation. You could travel at relativistic speeds, aging only a few years while a century passes on Earth, and emerge into a future where your disease can be treated. This would require technology we do not have. It would require trusting that the future society would be willing and able to help you. It would require accepting permanent separation from everyone you love. But it is not physically impossible. The laws of nature permit it. Another scenario involves existential patience. If you wanted to see how human civilization develops, if you wanted to witness the long-term future of our species, time dilation would allow it. You could skip forward through millennia, sampling different eras, watching the grand sweep of history unfold. But again, you could never go back. Each jump forward would be permanent. You would be an observer only, unable to return to any era you had left behind. The asymmetry between past and future time travel is not just a technical limitation. It reflects something deep about the nature of time itself. The past is fixed. It has already happened. It is recorded in the structure of the universe, in the arrangement of atoms and the state of light cones, and it cannot be changed. The future is open. It has not happened yet. It exists only as possibility, as potential, as the set of states that the universe might evolve into. You can travel toward it because it is not yet determined. You can even skip over parts of it, allowing it to unfold without your participation. But you cannot travel away from it, back toward a past that no longer exists in any physically accessible sense. Let me tell you about the philosophical implications, because they are profound. If backward time travel is truly impossible, then the past is truly gone, not hidden, not inaccessible, gone. The moments you have lived are not stored somewhere, waiting to be revisited. They do not exist in any physical sense. They are patterns that the universe once exhibited but exhibits no longer. This is a stark view of time. Many people find it disturbing. We remember the past so vividly, it seems so real in our memories. How can it not exist? But memory is not the past. Memory is a present state of your brain, a pattern of neural connections that encodes information about events that no longer exist. When you remember your childhood, you are not accessing your childhood. You are activating a representation of your childhood stored in your current brain. The actual events are gone. Some philosophers have proposed that all moments of time exist eternally, that the past and future are just as real as the present, that we merely experience them sequentially due to our position in the four-dimensional block of space-time. This view, called eternalism or the block universe theory, is compatible with the mathematics of relativity. But even if eternalism is correct, it does not enable backward time travel. The block universe is static. It does not change. Each moment exists eternally, but nothing moves between moments. You cannot travel from one slice of the block to another. You simply exist at your particular location in space-time, experiencing that moment and no other. The block universe might provide metaphysical comfort. Your past might exist eternally, frozen in the structure of space-time. but you cannot visit it. You cannot experience it again. You cannot change it. In every practical sense, it is gone. Let me tell you about what science fiction gets wrong, because the misconceptions are deep and widespread. Science fiction treats time as a dimension you can move through freely, like the 3 dimensions of space. Want to visit ancient Rome? Just set the dial and go. Want to see the far future? Punch in the coordinates. Time becomes a highway with exits at every era. This makes for good stories. But it is not how time works. Space and time are not equivalent, despite being unified in space-time. You can move freely through space, forward and backward, left and right, up and down. You cannot move freely through time. You can only move forward at varying rates depending on your velocity and gravitational environment. This asymmetry is not a contingent feature of our universe that might have been different. It is built into the structure of space-time itself. The metric of space-time, the mathematical object that describes its geometry, treats time differently than space. Time has a different sign in the equations. Moving through time works differently than moving through space. Science fiction also gets causality wrong. Stories often show characters changing the past and then experiencing the changed future. But this presumes a meta-time, a higher order time, in which changes to the past propagate forward. There is no such meta-time in physics. There is only time, and time does not allow changes to propagate backward. If you could somehow change the past, the change would not ripple forward to create a new future. The change would create a logical contradiction, a universe that contains incompatible information, an incoherent state that physics does not permit. The grandfather paradox is not a puzzle to be solved. It is a reductio ad absurdum, a demonstration that the premise leads to contradiction and must therefore be false. You cannot kill your grandfather because you cannot travel to the past. The impossibility of the paradox is evidence for the impossibility of the travel. Some science fiction introduces branching timelines to avoid paradoxes. Change the past and you create a new branch. The original timeline continues unchanged. The new timeline develops from the point of change. This is logically coherent, but it is not time travel in any meaningful sense. You are not changing your past. You are creating a new universe that resembles your past and then changing that. Your actual history, the timeline you came from, remains unaffected. You have not traveled through time. You have traveled between parallel universes. And we have no evidence that parallel universes exist. The many worlds interpretation of quantum mechanics suggests they might, but this is speculation, not established science. Building hopes for time travel on unproven interpretations of contested theories is not physics. It is wishful thinking. Now let me tell you why, despite everything I have said, I find the impossibility of time travel not a source of despair, but a source of wonder. And let me tell you why the universe's prohibition on visiting the past might be the very thing that makes existence meaningful. We dream of time travel because we have regrets. We made choices we wish we could unmake. We lost people we wish we could see again. We witnessed events we wish we could change. The fantasy of time travel is the fantasy of a second chance, an opportunity to correct our mistakes, to heal our wounds, to undo the damage we have done and the damage that has been done to us. I understand this longing. I feel it myself. There are moments in my life I would give almost anything to revisit. Conversations I wish I had handled differently. Decisions I wish I could remake with the knowledge I have now. People I wish I could see one more time just to say the things I never said. But the impossibility of time travel means that every moment matters. Precisely because you cannot go back, precisely because the past is forever fixed, the choices you make right now have weight. They have consequence. They are real in a way they could never be if you could simply undo them later. Consider a universe where time travel was possible, where any mistake could be erased, any decision reversed, any loss undone. In such a universe, would anything matter? Would choices have meaning? Would love have depth? If separation could always be undone? Would achievement have value if failure could always be retroactively prevented? I think not. I think the weight of our choices comes precisely from their permanence. We cannot go back. We cannot undo. We must live with the consequences of our actions, and this necessity gives those actions their significance. The impossibility of time travel is the foundation of meaning. This is not merely philosophical speculation. It connects to the deepest structures of physics. The arrow of time, the increase of entropy, the flow from past to future. This is not an inconvenience. It is the precondition for complexity, for life, for consciousness, for everything we value. Let me explain. In a universe without an arrow of time, nothing would happen. Events would not have before and after. Causes would not produce effects. Processes would not unfold. The universe would be static, unchanging, a frozen block of space-time with no development, no evolution, no history. The arrow of time allows things to happen. It allows stars to form from hydrogen clouds, burn through nuclear fusion, and explode as supernovae, scattering heavy elements into the cosmos. It allows planets to coalesce from debris, cool, develop atmospheres and oceans. It allows chemistry to become biology, simple life to become complex, evolution to sculpt organisms of astonishing intricacy. It allows you to exist, to think, to wonder about the nature of time, and to feel the poignancy of its passage. The second law of thermodynamics, which prevents backward time travel, is the same law that drives all the processes that created you. Entropy increase is not just about disorder. It is about the universe exploring its possibilities, moving from less probable states to more probable states, generating complexity along the way. Life exists in the flow from low entropy to high entropy. We are dissipative structures, patterns that maintain themselves by channeling energy from low entropy sources to high entropy sinks. Without the arrow of time, without the entropic gradient, without the irreversibility that prevents us from traveling to the past, we could not exist at all. So when I contemplate the impossibility of time travel, I do not feel constrained, I feel grateful. The same laws that prevent me from revisiting my past are the laws that allowed me to have a past worth revisiting. The same arrow of time that carries me inexorably toward death is the arrow that made my life possible in the first place. Let me tell you about something else that follows from the impossibility of time travel. The importance of the present. We spend so much of our lives dwelling in the past or anticipating the future. We replay old events in our memories. We worry about events that have not yet occurred. We treat the present moment as merely a transition, a bridge between what was and what will be. But the present is all that exists. The past is gone. It cannot be recovered. The future has not arrived. It cannot be experienced until it becomes the present. Only now is real. Only now is accessible. Only now is the moment when you can act, when you can choose, when you can live. The impossibility of time travel is a reminder of this truth. You cannot escape the present by fleeing to the past or jumping to the future. You must be here now in this moment because this moment is all you have. This is not a limitation. This is a gift. The present moment, however brief, is the arena of all possibility. It is where decisions are made, where love is expressed, where creativity flourishes, where life is lived. The past constrains it. The future will inherit it, but only the present is alive. Let me tell you about the scope of time, because understanding our place within it can transform how we think about these questions. The universe is approximately 13.8 billion years old. It will continue for trillions of years more, perhaps forever. Stars will burn out, galaxies will drift apart, black holes will evaporate through Hawking radiation. The cosmos will become cold, dark, and empty. Against this backdrop, human life is vanishingly brief. A human lifespan of 80 years is to the age of the universe as 1 second is to 500 years. We are mayflies, flickering into existence for an instant before vanishing forever. Some find this depressing. I find it liberating. We cannot comprehend eternity. We cannot meaningfully experience billions of years. Our minds are adapted for human timescales, for days and years and decades. This is the scope of our existence, and it is enough. The fact that we cannot travel through time, that we are bound to our brief moment in cosmic history, is not a tragedy. It is the definition of being human. We are creatures of the present, shaped by the past, pointed toward the future, but alive only now. And what a now it is. We exist at a remarkable moment in cosmic history. The universe is old enough to have produced heavy elements, planets, and life, but young enough that stars still shine and complexity still flourishes. We are part of the first generation of beings, as far as we know, to ask these questions, to peer into the deep past through telescopes, to contemplate the far future through physics. We cannot visit the past, but we can study it. We can look at ancient light from distant galaxies and see the universe as it was billions of years ago. We can examine fossils and reconstruct the history of life on Earth. We can analyze the cosmic microwave background radiation and learn about the first moments after the Big Bang. We cannot visit the future, but we can influence it. Every choice we make, every action we take, sends ripples forward through time. We shape the future by how we live in the present. Our decisions matter, our lives matter, not because we can travel through time, but precisely because we cannot. Let me tell you about legacy, because this is the only form of time travel available to us, and it may be enough. You cannot travel to the future, but your actions can. The words you speak, the things you create, the love you give, the children you raise, the ideas you share, all of these travel forward through time without you. They persist after you are gone. They affect people you will never meet in times you will never see. This is how humans have always transcended the limits of our brief lives. We write books that are read centuries after we die. We build structures that stand for millennia. We create art that moves people across generations. We raise children who raise children who raise children, an unbroken chain of life extending into the distant future. When I think about what I leave behind, I do not feel the need for time travel. I feel the need to live well now, to create things of value now, to love generously now, so that my effects ripple forward long after I am gone. The philosophers and scientists of ancient Greece still influence us today, 2,500 years after they lived. Shakespeare still moves audiences 4 centuries after his death. The Buddha and Jesus and Muhammad still shape billions of lives millennia after they walked the earth. These people did not need time machines. They achieved a kind of immortality through the lasting impact of their lives. You do not need a time machine either. You are already sending messages into the future. Every action, every word, every choice. The question is not whether your effects will persist. The question is what effects they will be. Let me conclude with a thought about why we ask these questions at all. The dream of time travel is ancient. Every culture has stories about visiting the past or glimpsing the future. We seem to be hardwired for temporal longing, for wishing we could escape the relentless flow of time that carries us toward death. But perhaps this longing, like so many of our longings, points to something other than what it seems to point to. We do not really want to change the past. What we want is to be at peace with the past. We want to forgive ourselves for our mistakes, to grieve our losses fully, to integrate our experiences into a coherent narrative that allows us to move forward. We do not really want to know the future. What we want is to feel secure about the future. We want to know that our efforts matter, that our loves will endure, that our lives have meaning that extends beyond the boundaries of our own brief existence. Time travel is a fantasy solution to real human needs. It addresses the symptoms rather than the causes. It imagines that technology could solve what are fundamentally emotional, psychological, and spiritual challenges. The real work is not to escape time, but to make peace with it, to accept that the past is gone and cannot be changed, to accept that the future is uncertain and cannot be controlled, to find meaning and purpose in the present, the only moment that is ever real. Physics tells us that backward time travel is impossible. I have explained the reasons at length. The laws of thermodynamics, the structure of causality, the nature of space-time itself, all conspire to prevent us from visiting the past. But perhaps physics is telling us something more than a prohibition. Perhaps it is telling us how to live. Perhaps the impossibility of time travel is a message about the nature of existence. A reminder that life is precious precisely because it is brief, that choices matter precisely because they cannot be unmade, that love is valuable precisely because it is vulnerable to loss. The universe has given us one direction through time, forward, always forward, into the unknown, toward the uncertain, with no possibility of retreat. This is not a prison. This is an adventure. The past is a story we tell ourselves, preserved in memory and record, but no longer real. The future is a possibility we create through our choices, not yet real, but shaped by what we do now. The present is the only reality we ever have, the thin edge of existence where all life is lived. We cannot travel through time, but we can live fully in the time we have. We can learn from the past without being trapped by it. We can work toward the future without being paralyzed by uncertainty. We can embrace the present as the gift it is, the only moment where anything can happen, where anything can change, where life can be lived. The universe has told us no. No, you cannot visit the past. No, you cannot undo your mistakes. No, you cannot see your loved ones who have died. But the universe has also told us yes, yes, you can move forward. Yes, you can create meaning. Yes, you can love and build and dream and strive. Yes, you can make your brief moment count. Time travel will never exist. And perhaps that is exactly as it should be.